should consider also the price of the hydrogen, just as mentioned before, and also how the hydrogen is produced. In its production, how much the greenhouse emission is produced for each weight or volume of hydrogen. As a whole, is the world benefited or is suffered from this kind of production is also the important question to be answered. So I think as a whole, if we consider the problem, we should consider the thing in a bigger scale, and take the whole thing into consideration. And of course, the hydrogen, the freedom car, the hydrogen-powered fuel cell cars is a car that would be finally replace the present car. But the time for it, or the step for it, I think many questions are still to be discussed or considered. Only to consider one point or one question might not be sufficient to answer the whole question. Well, that's my suggestion. Yeah.
Thank you, Professor Wang. I will also mention that when you think about transportation, it's so critical to modern society. And in fact, if you look at industrial countries, many industrial countries, 1/3 to 1/2 of all the energy consumed is not to make anything, not for manufacturing products or anything, but simply to transport people and goods. So there's a tremendous amount of energy that's consumed for transportation. And if you can take CO2 emissions out of the picture from the tailpipe, and of course, as Professor Wang said, you need to consider when you produce the hydrogen to ensure that you don't emit even more pollutants and CO2. We need to consider carbon sequestration and so forth. That's one of the main advantages of taking CO2 emissions and other emissions out of the tailpipe equation, where we can more easily reduce or control emissions in a centralized manner. Any other comments? Okay.
It's a very good comment.
Yes. Mario had one more comment?
Yeah, just coming back to the cost point. The impression is that the evaluation from industry are they're carried out as business as usual. They're looking at new technology. They're considering the approach as the usual, a new car, a new vehicle. They don't take into account, as the case for Europe, of the premium advantages for an emission-free car. We have free parking. We have no restriction for the access to the city center. This is not considered in the cost evaluation normally, because they are comparing the range, for example, could be a problem for such electrically driven vehicle using fuel cells or batteries or something. But they have a big advantages for most cities. Particularly in Europe, we don't need so long range. But the impression is that, as a global point of view, there is one car under consideration. But in reality, they are not really niche. They could be also large share of a market. But the impression is that they are still starting, not consider that probably we will need, in the near future, the shorter range car with other advantages. Probably we have to close the cities, what we are doing now. And the cities are not allowed to be circulated to any type of car. They must be absolutely emission-free. And emission-free premium or label will be one advantage, will be costly also. It's a general question.
May I just add my very strong agreement with what has just been mentioned. It would seem to me personally that one of the strongest arguments for the hydrogen-powered car is that it will reduce the amount of it will reduce the amount of city air pollution. you may get the CO2 production and pollution in other places, but at least the short-term advantage is to reduce the air pollution in city areas, and as an immediate advantage, this would seem to be highly desirable, which would then imply that maybe the automobile with a shorter range, particularly useful in driving from suburban housing to cities and back again, may be really one of the key objectives that we may all be working towards.
Well, just to support this comment, it's, in Europe we had carried out many surveys as a automotive industry, and we have numbers that which there's so niche markets for short-range vehicles is measurable in terms only considering major cities in European Union countries. They can be summed up in terms of million of cars needed, because the average range in Europe for each trip or daily trip is below 30 kilometers, and more than 70% of the travels are below this range. It means that 500 kilometers is for multi-purpose cars, but normally they are much less than 10% of the overall needs of the overall application for private sectors. This was why there was strong inputs and strong just work in developing alternative fueled vehicles, more specialized vehicles, because only for passenger cars and also for commercial vans, we have a range of 7 to 8 million technically potentially accessible market for these short-range vehicles.
Thank you, Mario. So now we have lunch, which I think everyone's been waiting for. And so we'll meet back here at 1:30, so we'll start about 15 minutes late. And I do want to remind people that we have sign-up sheets for reserving time at the conference rooms. Part of the objectives, as Pier Paolo mentioned, of this conference at the end is to submit proposals that would be considered by the IPHE. So on Wednesday, we'll have a wrap-up session with some more explanation on the process of how to go about submitting proposals, and we really like to encourage all the interaction by the technical experts from around the world during the next couple of days. So thank you and enjoy lunch.
I'd like to start out this afternoon with an overview talk about reversible onboard storage. It will be presented by Andreas Whittle from University of Freiburg.
So you can use this. Instead of the pointer, you can see, you can use this. Okay?
Okay, I'll try to do
And
that.
to go ahead with this, and to go back like that, okay?
Okay. Here I go ahead. Yeah,
And
okay.
back, okay? And hold it, otherwise it falls down.
Okay. So good afternoon, ladies and gentlemen. Thank you, Greg, for the introduction. I have the pleasure to give here an overview talk of the state of the art in hydrides. I changed that title a little bit. It was metal hydrides before. Now I would prefer to call it hydrides. I will start with the standard model we are using for metal hydrides, just to remind you about them. the basic concepts. And I would like to say some words about thermodynamics. And after that, I would like to switch over to the challenges and the challenges of new materials and the problems remaining with the materials we know. And I divided that up in metal hydrides, in magnesium hydride, aluminum hydride, then the alanites, the borides, the amides, and combinations of partially positively charged hydrogen with partially negatively charged hydrogen, and I will end with the conclusions. Now, in order to start with the standard model, you can see here this figure goes back to 1932, and that's really something we can call a standard. That's the way we look in an energetic picture on the hydrogen absorption in a metal. So we have on the blue line here, we have a hydrogen molecule and the metal, and on the red line, far from the surface, we have two hydrogen atoms and the metal. And when the hydrogen molecule, the metal, approaches, it finds itself in a first adsorption state here, the so-called physisorped state, and from there we have usually an activated process where two hydrogen atoms start to separate and then bind to the metal, and we get into the chemisorped state. And of course, in order to overcome this activation barrier, there is some energy required, and usually we have to heat up the sample. Only in cases where we have no activation, it goes directly into the chemisorped state. And from the chemisorped state, the hydrogen atoms then can enter the lattice in some metals and diffuse on the interstitial sites. And as you can see here on the figure, the chemisorpted state and the first subsurface state are usually on a lower energy than all the other states in the metal. So thermodynamically, we start with a dissolution of hydrogen, with a solid solution of hydrogen in the metal. The hydrogen diffuses more or less freely in the metal lattice on the interstitial sites and overcomes in the jump from side to side a certain activation barrier that limits the diffusion, and we have almost no interaction between the different hydrogen atoms in this state, and there is a certain volume expansion due to the interaction of hydrogen with the surrounding atoms. It breaks partially the bonds between the metal atoms, and this volume expansion is in this state proportional to the amount of hydrogen in the lattice. And now, due to the volume expansion, we can define that as an active interaction between the hydrogen atoms. We have a phase transition, and above a certain concentration indicated here, we go into this phase transition, and the solid solution phase directly jumps into the hydride phase, and the hydride phase grows through the lattice in an ideal case. Now, this phase transition occurs, of course, only up to a critical temperature indicated here. Above this temperature, we do not have a phase transition anymore. Now, the phase transition, as I said this morning, one consequence is that the pressure during the absorption remains almost constant. That this is a very appreciated property for hydrogen storage, of course, because it means that we can fill our hydrogen storage without significantly increasing the pressure in the system. We can describe the pressure concentration relation with this Van 't Hoff equation, where we have delta H, the logarithm of pressure is proportional to delta H 0 over RT minus delta S 0 over R. That means the slope here is given with delta H, and the interception point is given by the entropy. Now, in most cases, the entropy change is proportional to the standard entropy of hydrogen. That is just because we are forming from a gas a solid, and so the solid has almost no entropy compared to the gas, and therefore we can, in a first approximation, use the standard entropy of hydrogen as an From the Van 't Hoff equation, we can calculate in a certain range the pressure as a function of the temperature. And of course, for an application, it would be interesting to have the equilibrium pressure at the desired equilibrium pressure at the working temperature. But a storage system has to be laid out for the maximum possible temperature it can feel, and that means the pressure increases quite quickly if we increase the temperature, and especially the pressure increases very quickly if we are in the beta phase, in the hydride phase here, and dissolve some hydrogen in the hydride phase. This is a difficulty we have to overcome for an application. Now we have several rather simple models to estimate the amount or to calculate the amount of hydrogen we could absorb in a metal. There are certain criteria which have to be fulfilled. One is that the interstitial site has to have a certain size, otherwise it's not occupied with hydrogen, and this size, the radius has to be larger than or greater than 0.37 angstroms. Then a second criteria is that the distance between two occupied sites with hydrogen has to be at least 2.1 angstrom. I will show you examples where this is not the case. Now, if we assume that this would be always the case, we can calculate the theoretical maximum volumetric hydrogen density in such a system, and that is 245 kilograms per cubic meter. Now, this is interesting because the best hydrides, or the hydrides with the highest volumetric density we know today, have about 150 kilograms per cubic meter of hydrogen. So there is still a huge potential of improvement if this criterion here really applies to all the systems. And in order to estimate the number of hydrogen atoms we can bring into a lattice, we count the number of interstitial sites for which these two criterions apply, and then we have the maximum number of hydrogen in the lattice. Now, the second, that was the amount of hydrogen in our system. The second important parameter, of course, is the stability. And here again, we have empirical models. The first one is the Midema model, the model of reverse stability, which simply means the more stable an alloy is, the less stable is the hydride, and the other way around. And that is based on the assumption that when hydrogen enters the lattice, it has to partially break the bonds between the metal atoms. That's why we have here this factor 1 minus F, and that is the disadvantage of this model. There is no ab initio way to calculate this parameter F, so it describes systems which are similar or known from experiments, but it doesn't allow us to calculate directly stability of a certain intermetallic compound. Another model is based on the imaginary binary hydride, so it's a model which describes the stability of an intermetallic based on the stability of the hydrides of the elements. And there is, of course, also an electronic part involved in hydrogen absorption, because if we absorb a hydrogen atom, it means we introduce a proton, but at the same time we add an electron to the band structure of the metal, at least for very small concentrations, that's the case. And based on that, Ronald Greason has developed a semi-empirical model for the stability based on the local band structure model, and the parameters in this model are the width of the D band in the metal and the energy difference between the Fermi level and the hydrogen S band, and the distance of the center of the interstitial sites to the neighboring atoms. So, and based on this model, it was possible to calculate the enthalpy of formation for infinite dilution for the elements quite accurately, as you can see in this figure here. So thermodynamically, I have shown that before, due to this phase transition, we see a plateau, and we can describe the formation, or here in this case, the dissociation of a hydride, the decomposition of a hydride with the Gibbs free energy. And if we decompose the hydride, delta H is positive and delta S is positive. If we form the hydride, it's the other way around. And based on that, we find the Van 't Hoff equation, and with the Van 't Hoff equation at a pressure equal to P0, we can describe the decomposition temperature. So this will be very important for the discussion of other types of hydrides I will talk later on about, because often in not perfectly reversible system, the decomposition temperature is the important parameter. But once again, the decomposition temperature is only a real measurement if we are in equilibrium and if the pressure is equal to P0, which means if the pressure is 1 bar or 10 to the 5 Pascal. Now, the Van 't Hoff equation of many systems looks like that, and you can see in general these lines all point to the same, interception point on the axis, which is again the 130 joules per Kelvin mole standard entropy of hydrogen. And we have a wide range of intermetallics and metals which cover a range from something like -20 to 500 degrees centigrades at 1 bar pressure. Now, thermodynamics tells us, beside of the plateau, that tells us a second important parameter, and that is about the heat evolved during the absorption or desorption. And this heat is once again is delta Q, is the standard entropy of hydrogen times the temperature. And if we put this heat in relation to the heat of combustion, the higher heating value of hydrogen, then we find this simple relation here, that the ratio of the heat necessary to desorb the hydrogen divided by the higher heating value is 4.6 times 10 to the minus 4 times T. And that means as long as we are working at a temperature below the equilibrium temperature, the ambient temperature, our environment can provide the heat to desorb the hydrogen. As soon as our working pressure requires a temperature above the environment, we have to deliver this heat to the system. And here in this figure you can see how this how this ratio increases with temperature. And for example, if we are working at something like 300 degrees centigrade, so about the magnesium hydride temperature, it already requires almost 30% of the heating value just to desorb the hydrogen. And this is, again, a general parameter of all systems which make a gas-solid transition of the hydrogen. Now, I would like to say some words to the challenges of new systems. Here is a list of hydrides, and there are a few things I would like to point out here. So this list starts with lanthanum nickel 5 H6 with 1.49 mass percent of hydrogen. It goes up to lithium boron hydride with 18.51 mass percent of hydrogen. So you can see that's about the limit. We do not know materials which show a higher mass percentage of hydrogen than 18.5. And in between we have, for almost any value we can find, corresponding hydride. Now, the last column here shows you the decomposition temperature. And it's very interesting to notice that the decomposition temperature is in no relation to the mass percentage of hydrogen. There are very, very unstable hydrides, like, for example, lithium aluminum hydride, or even ammonia is very unstable in equilibrium. With a very high mass percentage. And this is just a rumor that complex hydrides or hydrides with a high hydrogen storage capacity are necessarily stable. It is just because until now we have mainly, or let's say the chemists have mainly investigated stable compounds because they were interested in stable materials in the lab. But there are plenty of hydrides around which show a very high mass percentage but aren't stable at all. And we can put it in another relation with the volumetric hydrogen density, and again there is no relation between the volumetric hydrogen density and the decomposition temperature. So this is a very positive sign, because that means it's not hopeless to look at materials with a very high hydrogen density. They could still work at room temperature if we find the right ones. Now, sorry, that was too fast. Now I would like to say first something about metal hydrides. Where are the challenges on metal hydrides? Always in view of gas phase storage. And then I will go on with magnesium, aluminum, the alanides and the borides, the amides and the imides. And I will say something about the mixture of differently charged hydrogen. Now we have seen how the maximum capacity is defined in metal hydrides, and BCC alloys are especially interesting because the number of interstitial sites in these alloys is, compared to FCC and HCP, much larger. So there are more interstitial sites per metal atom available in these structures. And Etsuo Akiba has studied them since quite a long time, and he also found interesting systems with a high amount of hydrogen in the lattice. The big problem until now is that this first plateau, which isn't shown here, is always at a very low pressure. It's always a very stable hydride. And of course the challenge is to find methods to decrease the stability of this first plateau. By the way, this figure here shows you vanadium, from vanadium to vanadium H1 and vanadium H2. That is somehow the model system of a BCC hydride. But I guess we will hear some more information about that from Etsuo Akiba. Then the next possibility to increase the hydrogen density in metals, of course, is to put the hydrogen closer than what the criteria tells us, closer than the 2.1 angstrom. And there are also indications that this is possible in certain systems. For example, in this rare earth transition metal indium hydrogen system, it was found that hydrogen in some cases is closer, in some sites is closer than 2.1 angstrom due to the significant charge transfer on the lanthanum. Now, the open question here is it possible to occupy all these sites which are closer than 2.1 angstrom? Because until now it was always studied on only partially hydrided systems. So it may well be that in one case, one site here is occupied, and in another unit cell the other side is occupied, but they probably never occupied at the same time. Then the next big challenge, of course, is magnesium hydride. That is nothing new. There is work going on magnesium hydride since many, many years. A very interesting approach appeared last year, where lithium hydride was mixed with silicon and magnesium hydride was mixed with silicon, and it led to a much lower desorption temperature. The reason for that is simply because of the stability of the corresponding silicate. The desorption occurred at a lower temperature, or the formation of the metal with the compound of the metal with the silicon leads to a less stable hydride. Now this is interesting, especially if such a system may be reversible, and in case of, if I'm not mistaken, in case of lithium it is reversible, but in case of magnesium it wasn't shown until now, the reversibility. But that should be furthermore investigated. Then there is always, already since quite a time, this discussion about the metal-stable magnesium hydride phase. When you compare magnesium and magnesium hydride with titanium and titanium oxide, there is a strong similarity in the structures. And titanium oxide forms this anastase structure, but this structure wasn't found experimentally for magnesium hydride until now. However, theoretical calculations predict a much lower stability of the hydride in this phase. And therefore, of course, it would be interesting to synthesize this magnesium hydride phase and measure the properties of that. Now, the next very interesting system is aluminum hydride. That was investigated also recently by Gary Sandrock and co-workers. And the first observation was that the particle size or the kinetics of the hydrogen desorption is very much particle size dependent. So the smaller the particle size, the faster the desorption. This is not really very surprising. And then aluminum hydride was combined with lithium hydride, and this lowered also the desorption temperature. And the desorption temperature, as you can see in this figure here, is around, let's say, somewhere between 100 and 150 degrees centigrade. So in an interesting range. Now, when you calculate the decomposition temperature of aluminum hydride based on the heat of decomposition, then it is far below 0 degrees centigrade. So this means aluminum hydride is not really stable at room temperature. It's just kinetically hindered in the decomposition. And, but it has a very nice property. You can handle it in air, and it doesn't start to decompose, and that is due to the aluminum oxide film surrounding all the grains of aluminum hydride. So now there is again a lot of potential to improve this desorption behavior. Principally, it could work at room temperature already. However, on the other side, we have to control somehow also the spontaneous decomposition because, as I said, it is not stable at room temperature, and if it would, for some reason, spontaneously decompose, then of course it would, in the storage system, liberate all the hydrogen. In the isothermal desorption, it shows two different slopes, and the two different slopes correspond to two activation energies. One is 68 kilojoules per mole hydrogen, and the other one is 91 kilojoules per mole hydrogen. And you will see later on the alanates, these values are always very, very similar to the values for the activation energy for all such ionic compounds. Now that brings me to the next subject, that is complex hydrides. You know that boron and aluminum together with hydrogen and an earth or alkali earth metal form complex hydrides, and some of these complex hydrides have very interesting properties. And I told you this morning, the whole research was started after Boris Bogdanovic's presentation in 1996 because sodium aluminum hydride, correctly catalyzed, showed a very nice behavior, hydrogen desorption behavior, just like metal hydrides do, with two plateaus, and it was a completely reversible system. So therefore, a lot of research was started on that, especially in order to catalyze sodium aluminum hydride hydrogen desorption. Now, when you calculate the activation energy again for the non-catalyzed and for the catalyzed sodium aluminum hydride, you notice that the catalyzed sodium aluminum hydride has an activation energy for the hydrogen desorption of about 80 kilojoules per mole. So again, it's in the same range as I showed before for aluminum hydride, and many others have values in this range. And there was, you can see here, a significant reduction of the activation energy due to the catalyst. Now the question is still how to efficiently apply the catalyst, and here is one figure on two differently catalyzed sodium aluminum hydride samples and one non-catalyzed, and you can see how the catalyst significantly lowers the desorption temperature. But you will hear much more about that from Ferti Schütt afterwards. Now, one of the open questions in sodium aluminum hydride is the mechanism of the hydrogen desorption. But this is true in general for complex hydrides. Very little is known about how they desorb the hydrogen and even more how they absorb the hydrogen. That is a completely open question. It is for sure that hydrogen has to be transferred between different atoms in the structure in order to form the intermediate compound, and at the end hydrogen binds to the other element, and this is also true for all the complex hydrides. The hydrogen at the end is no more on the same element as it was in the beginning of the structure, and that means in order to make it reversible we always have to overcome the barrier to dissociate this, in this case here sodium aluminum hydride, in other cases lithium hydride. Energetically, it looks like that. We have a high heat of formation of 113 kilojoules to the sodium aluminum hydride, and then heat of decomposition of 37 kilojoules into the intermediate state, another one of 23.5 kilojoules to the sodium hydride. This is not per mole of H2 here, that is always for the corresponding amount of material. Now, the basic difference between metal hydrides and complex hydrides is, as I mentioned, the hydrogen ends up at the end in the gas phase and on another element, and we form more than one phase. And that's why we have to look always at the decomposition temperature here, and we do not, the Van 't Hoff equation does not apply anymore in order to calculate the decomposition temperature, because the system is not in this, in the energetic sense, not completely reversible. Now, okay, I'm almost over with my time. I will just show you one example of lithium boron hydride, because that's the complex hydride with the highest mass percentage of hydrogen. And here on the bottom in the blue line you have the decomposition of lithium boron hydride of the pure sample, and the red one is a catalyzed sample. And you can see also with a catalyst in lithium boron hydride we can reduce significantly the desorption temperature. However, this is desorption into vacuum, and this measurement doesn't tell us directly the decomposition temperature. It's a mixed information of kinetics and stability. The more important open question with borohydrides is the reversibility, and that's an experiment we did on lithium boron hydride. Here is first we increased the temperature, we desorbed the hydrogen. You can see that here we desorbed 3 of the 4 hydrogen, and then we applied a high hydrogen pressure and reduced the temperature, and we reabsorbed the hydrogen. And here are the corresponding X-ray diffraction patterns for the initial compound, for the desorbed compound, and here for the reabsorbed hydride. And you can see the reabsorbed hydride structurally looks even better than the initial compound. So this is the other rumor that borohydrides are intrinsically not reversible. That is not true. Borohydrides may be reversible, at least partially, just like the alanates. However, it all depends on what phases are formed and if the elements remain close together in the 2 phases formed in the desorption of the hydrogen. So, yeah, I should stop. I'm sorry. Okay, I will skip the amides. Sorry for that. Maybe just a short word. Ammonia is also a very interesting hydrogen storage system, especially because it can be liquefied under pressure at ambient temperature. The only problem is it is a poison and it is toxic, but there are also ways to bind ammonia without adding too much of additional weight, and then we end up with a system which isn't toxic anymore. Okay, so that brings me to the conclusion. I showed you that solid hydrides with a gravimetric hydrogen density of up to 18 mass% exist. Volumetric hydrogen density of all solids is larger than 80 kilograms per cubic meter. That is also a very nice property. There is no relation between the gravimetric hydrogen density and the decomposition temperature. But there are a lot of open questions, so we do not know a lot about the desorption mechanism in complex hydrides. The desorption rate is sample size dependent. It is, in most cases, and Gary Sandrock has published that more than 20 years ago. Yes, it's a problem of the heat transfer. So all these results which show a very high rate of hydrogen absorption or desorption are mainly done on small samples, and that's the reason why they have such high rates. Okay, then reversibility and synthesis of complex hydrides is a problem. The destabilization is a problem. Stabilization and catalytic decomposition of unstable hydrides, that is another really important challenge. And of course, finally, we have to answer, is the reaction of a multi-phase compounds to a complex hydride ever really complete? So that means, can they ever be really reversible? So I'm sorry for taking too much time, and I thank you for your attention.
We have time for a couple of quick, well, we don't, but we should take a couple of quick questions. Quick question.
What about the thermodynamic properties of the metals as one reduces the particle size very greatly? For example, if you get down to 3 or 4 nanometer diameter, the surface free energy then becomes an increasingly important component of the overall free energy of the metal. So my question is, has any study been done in which the particle size of the metal is considered as a variable parameter in the thermodynamic properties of the metal with respect to reaction with hydrogen? Not talking about kinetics here, talking about change in thermodynamic properties due to increased contribution of the surface free energy to the overall free energy of the metal.
Yes, yes, such studies have been done mainly by Rainer Kirchheim's group in Göttingen, and we also did investigation of hydrogen absorption in palladium clusters. The size has an important influence on the stability. As you mentioned, there are more surface sites and especially more subsurface sites in clusters. However, this change of the thermodynamics only takes place on clusters below about 3 to 4 nanometers. And they are usually extremely reactive, and it is possible to handle, for example, palladium, but for most other hydrides it's almost impossible to handle them anymore. And especially, of course, the surface also becomes very reactive to all the impurities which may be in the hydrogen, and therefore it is also a big challenge to work on that.
Thank you.
I think we better move on. So our next speaker will be, let's thank Andreas. Next speaker is Ferdi Schuth from Max Planck Institute in Mülheim, and he will be talking about alanates as potential hydrogen storage materials, state-of-the-art, and perspectives.
Thank you, Craig, and thanks to the organizers for giving me the opportunity to talk here. But I should say first that Boris Bogdanovich, who started the work on the alanate about 10 years back, should be standing here. He sends his best regards, but he doesn't like to travel to conferences anymore, and so I'm standing here today.
Use this as a pointer.
Where is the...
That's turned on.
Oh, it's turned off. Okay.
And to go ahead, press this one. And to go back, press that. Okay?
It's not working.
It should be, yes, there it is.
Oh, there it is. Okay.
Back, front,
Yep.
back.
So what I have my own table of requirements for the system, one of the reasons being that there are different requirements from DOE, Japan, the European Union, and I sort of collated my own table of requirements more or less just to say these are not chiseled in stone. You have to balance the requirements, I think, a little bit against each other. I've highlighted the really challenging one. I think it's the gravimetric storage capacity, it's the rehydrogenation time for the alanates, at least, or for complex hydrides. It's the enthalpic effect, which we can't get rid of, as Andreas Schüttel has told us. And I think price is an issue which we often underestimate. There are actually not many elements around which we can get at a price to have an overall price for our tank, for the material in the tank, which is, let's say, at 100 euros per kilogram of hydrogen, somewhere in this ballpark. So our choice is rather limited. Sodium, aluminum are in fact elements which we could use. Now I want to talk mostly about sodium alanate because I think that's the most advanced system so far, and at the end want to go to other alanates and also give some perspectives. I should also say in the beginning that I will never show a hydrogen desorption curve, because I don't consider this as a problem for the alanates anymore. Hydrogen desorption for the alanates in all the samples we are investigated are on the order of 1 hour, which is definitely sufficient for use in a car. The crucial issue is the rehydrogenation, and so I'm only showing hydrogenation curves. Just that we know what we are talking about. The sodium alanate, this is an old structure. It was an X-ray structure, and there is a recent neutron structure which is slightly different. The essentials are like the old structure, but this, I think, is the state-of-the-art structure for the sodium-aluminum tetrahydride. And then there is the intermediate phase, the hexahydride. There is actually two different phases. There is an alpha phase, which is plotted here, and there is a beta phase, which resembles the cubic cryolite, which convert into each other at about 250 centigrades. And in fact, the decomposition may be related to this phase change between the alpha and the beta phase of the hexahydride. But that's still an open question, I would say. How do you make the materials? The original work by Manfred Schwikardi, Boris Bogdanovich was a solution doping, but about 3 years later, Zidane and one of our chairmen, Craig Jensen, developed the ball milling procedure, which basically is the preferred method used nowadays. I think basically everybody working on sodium alanate and alanates is using the ball milling to synthesize the materials. This ball milling is in fact scalable. We have produced in our laboratory a 10 kilogram batch of titanium doped sodium alanate in 4 smaller batches, so 4 times 2.5 kilogram batches. That was not used as a hydrogen storage material, or only hydrogen storage was only a secondary effect. This was used as a thermochemical heat storage material for a Stirling motor. But the hydrogen adsorption, desorption properties of this 10 kilogram batch was pretty much the same as the hydrogen desorption, adsorption properties of smaller batches, which we typically produce on the several gram scale. This is not our optimized material, but a material similarly produced on the gram scale has roughly identical properties. So it's a scalable process. I would consider this as the most advanced method to prepare sodium alanate. We recently have developed a mill where we can, under hydrogen pressure, under about 100, 130 bars hydrogen pressure, mill compounds and record temperature and pressure in the vessel by a radio transmission device, because you cannot attach to a vibrating mill tubes and cables. And with this method, we actually start from sodium hydride, aluminum powder, titanium trichloride in this case as the catalyst, pressurize it to 80 bars, mill under the pressure, and you see that after about 2 hours, this is the pressure curve here, after about 2 hours, hydrogenation of the material is complete, and we have a titanium-doped sodium alanate. The big advantage of this method is actually the extremely fast kinetics. The kinetics of this directly synthesized material under hydrogen pressure milled is about as fast as for the materials which I would consider the best ones known before, which are the colloid materials, which we had described about 2 years ago and Maximilian Fichte had described 2 years ago, where you use titanium colloids. The direct doping under hydrogen pressure with titanium trichloride gives you roughly the same kinetics. It's all over in, I would say, less than 15 minutes, and the cycle stability is rather high for these materials. Catalysts, there is a wealth of materials investigated. Various different titanium compounds have been studied, various transition rare earth elements have been studied, carbon has been added, diamond powder has been added. There is a wealth of different materials, but I think when you look into the literature, there is pretty much agreement that the best catalyst is titanium compounds, and out of the titanium compounds, I think the colloids, titanium-13 colloids, are the best ones, but they are so outrageously expensive that you would never use them. And the second best choice is titanium trichloride, I think. Titanium trifluoride comes close. I have just plotted here a couple of different catalysts, the rehydrogenation rates for a couple of different catalysts, which were all prepared under the same conditions. This doesn't mean that vanadium tetrachloride is always worse than, let's say, titanium butoxide. Each of the catalysts may have its optimized synthesis procedure for the doped material, but if you do them all the same, this is roughly the sequence of activities we find. The best is the titanium nanoparticles. Titanium trichloride is rather good, and if you directly synthesize, the rate is like the titanium nanoparticle rate, so it depends on the method of synthesis. Alkoxides are certainly not as good, and basically most of the other catalysts which have been investigated are far inferior. That's what we thought until we re-examined some of the rare earth elements, and we actually found that scandium and cerium are superior to titanium. So these are all identically synthesized titanium trichloride, scandium trichloride, cerium trichloride. The scandium and the cerium have quicker kinetics than the titanium trichloride as catalysts, and especially for the scandium chloride, the capacity is basically at the theoretical limit. So it's 4.9% consistently over many cycles, reversible capacity at these rates. The other important thing, I think that's the field where we have still the most deficiencies, is low pressure rehydrogenation. Normally we do our rehydrogenation, as you see here, at a pressure of around 100 bars. This is not optimum because at 100 bars you typically have a cylindrical tank, which is difficult to pack in a car, and so you want to have 50 bars or even lower. And then kinetics for most of the materials reported are very, very slow. For the scandium and cerium-based materials, we have 2% storage capacity at 50 bars in about 10 minutes. And if you wait 3 hours, you again approach the theoretical capacity. So there is really room for improvement towards the low-pressure rehydrogenation with these materials. This is our most advanced system. I can't tell you what it is, but this is the quickest system we have, and I would say that this has met basically the requirement of fast rehydrogenation. I think the system is basically heat transfer limited. The yellow curve is the temperature, so the system was heated to 120 centigrades, then was pressurized with 110 bars roughly of hydrogen, and you see you have a temperature overshoot to 180 centigrades. And at that temperature, it's difficult to rehydrogenate the second stage, so the system has to cool down again. And while it cools down, it absorbs the hydrogen, and you see that it's basically over after 5 minutes, and the majority of the hydrogen has been absorbed, I would say, after 2 minutes. If the temperature would be stabilized, we are pretty sure that would be a rehydrogenation rate on the order of 2 to 3 minutes. For, in this case, the 3.2 is plotted. We have now 3.5. There is more catalyst in there, so the theoretical value, the expectation value is about 4.5. So we rehydrogenate about 75% of the theoretical capacity in this case. Mechanism, Andreas Züttl has already said that's one of the crucial questions or most difficult questions we are still facing. I think there is at least agreement on the state of titanium since roughly a year. We published an EXAFS TM Xane study, which was subsequently corroborated by almost similar data from the Brookhaven team and Maximilian Fichtner's group. The EXAFS spectra basically tell you that the state of titanium, the local environment of the titanium, does almost not change during cycling. After synthesis, rehydrogenated, dehydrogenated, the state of the titanium remains pretty much the same. If you look into more details, we have a whole series of different investigations. These are the Xane spectra, which are sort of fingerprints. You see that the spectra of the titanium in the sodium alanate resembles a titanium Al3 alloy. I wouldn't say it isn't a titanium Al3 alloy, but this is the closest resemblance. It's certainly not titanium metal. It's certainly not an oxidic compound. There is some probably disordered state of the titanium surrounded by aluminum neighbors. And based on this observation and TEM data and other data, we think what's going on in the system is after ball milling, we have sodium alanate, titanium as a high concentration in aluminum, and sodium chloride. When we decompose, we have titanium in the aluminum at a very low concentration because now the sodium alanate has decomposed to the aluminum, sodium hydride, and the remainder of the sodium chloride from the doping. And then it cycles back and forth between a sodium alanate and the dehydrogenated state, and the titanium basically just changes concentration in an aluminum matrix. This is what all the experimental evidence points to. This is the description. It doesn't tell you what's happening in the system. Actually, based on some of these EXAFS data, there are DFT calculations on the mechanism, or at least on part of what the titanium does. The DFT calculations point to titanium sites as responsible for hydrogen dissociation on the surface. It's a titanium centers in an aluminum environment where the hydrogen dissociates and is thus activated for the absorption process. And that's in line with isotope exchange experiments which we have performed. If we put sodium alanate in a deuterium environment, there is no scrambling, there is no HD formed. But if we put titanium-doped sodium alanate in a deuterium environment, we find HD in the gas phase, as seen here. After D2 dosing, we find HD in the gas phase. We have looked at this in more detail, calibrated the volumes, calibrated the amounts, and fitted kinetically. And if we analyze the data, this is an experiment at 60 centigrades, the result is that basically at 60 centigrades, the hydrogen from the bulk of the sodium alanate participates in the scrambling experiment. So the titanium provides the mechanism for hydrogen exchange, dissociation of hydrogen. I don't think this is enough to explain everything because we have massive mass transfer going on in the system, but this is certainly one role of the titanium, one role of the catalyst, that we have the dissociation. I just said mass transfer. I think this is still an open issue. Andreas Züttl again has said we have sodium alanate, it decomposes eventually into sodium hydride and aluminum. These grains are hundreds of nanometers in size, and they have to recombine to form a homogeneous compound again. And how that proceeds is still an open issue. I mean, it has been surface and bulk diffusion of the species has been discussed. alanes have been suggested as intermediates as well as a disodium aluminum H5 species, but there is so far no experimental proof that these species are really there. And I would say mass transfer is still an open issue for this system. I want to move to other alanates, briefly touch what we have there. Magnesium alanate is, I would say, except for lithium alanate, the second well-known system. It was structurally described by the group of Maximilian Fichtner. In this paper, which is cited, the THF adducts and ether adducts were structurally described. In a subsequent inorganic chemistry publication, also the neat compound was described. Synthesized by a metathesis reaction, we have found an alternative method which is our standard tool for making other alanates, which is ball milling of sodium alanate or lithium alanate with magnesium chloride or other halides, and then you make by again a sort of metathesis reaction the other alanates. I think the important message which Maximilian described in this paper and which we also found is that the titanium catalyzes the decomposition as in the case of sodium alanate. So the titanium action, the catalyst action, is at least transferable to the magnesium alanate system. I would say probably generalizable to all the alanate systems. Unfortunately, the thermodynamics for this system are unfavorable for hydrogen storage. It's not stable enough. It's way too unstable. There are other alanates. There is a poster on the potassium-sodium ALH6 outside. The group of Dymova has reported calcium alanate 3 years ago. I show you here 3 DSC traces for the ball-milled alanates: magnesium alanate, calcium alanate, lithium magnesium alanate. So it's again this metathesis reaction: sodium alanate plus the metal halide gives sodium chloride plus the metal alanate. You have the sodium chloride in there, but you can use the mixture to evaluate the thermodynamics. And unfortunately, the decomposition proceeds in steps, and all the steps for at least these 3 compounds are either exothermic or so weakly endothermic that it's not a reversible material under near ambient conditions, I would say. So magnesium, calcium, lithium, magnesium alanate, I think are not useful. The second stage of lithium magnesium alanate comes close to being reversible, but still for rehydrogenation, you can still calculate about 200 bars at room temperature. With that, I want to sort of summarize with the perspective. I would say that the sodium aluminum hydride system is almost optimized. I'm sure the system can be further optimized to give you the reversible capacity of close to 5% at rates which are below 5 minutes. Cycle stability we have done for some of our materials over not several hundred cycles, but beyond 100 cycles, 130 cycles without loss of capacity. I would say low pressure rehydrogenation at 50 bars is still an issue, because that would be very nice if one could achieve that. Other alanates which we have studied are unfortunately thermodynamically unfavorable. But the good news is that titanium catalysis works for the other alanates. And I think another piece of good news is that there are, if you look at the possible alanates, there is a whole wealth of alanates, and it's surprising how little is known about these, how little is known about the structure, about the synthesis, about the thermodynamics of these systems. And I think there may be treasures buried, so we shouldn't give up hope yet for finding a suitable material based on alanates which has a capacity higher than the 5.5 of the sodium alanate. With that, I want to thank you and thank the people who have contributed to the work.
Well, again, I should have mentioned this at the beginning of the session, that we should try to leave some time with the speakers. We got half an hour, but we should leave some time for questions at the end because the conference is kind of about interaction. So, and we've already run over the half an hour, but we should take a couple of questions, I think.
Thank you very much for the nice talk. My question is how you tried the microstructure analysis of the catalyst during the dehydrogenation and hydrogenation cycles.
I'm not quite sure what you mean by microstructure analysis. We have analyzed the dehydrogenated material in the TEM, where you see that the titanium is in the aluminum and not associated with the sodium hydride. We cannot analyze the hydrogenated material in the TM because our TM people then kill us because it dehydrogenates all over the place. We have done the EXAFs in all the different stages, which is also sort of a microstructural analysis, and the EXAF basically tells us it's titanium in the zero valence state in an aluminum environment in all stages of the cycle.
And I think you can install a glove box just around the TEM operator. You can do the modification, I think. So glove box, argon filled.
The problem is if you have a catalyzed titanium alanate and bring in, which is hydrogenated, and bring it into the high vacuum of the TM, it starts to dehydrogenate, and that means it spills all over the place, and then the column is ruined, and you don't want that. So our TM people are very reluctant, and I'm very reluctant to do that.
You said that scandium Cl3 and cerium Cl3 are superior to titanium Cl3. Do you think it's possible to explain it in terms of electronic structure of the different metals? Because then one could predict new catalysts eventually. Thank you.
It would be wonderful if we could, but since we don't even know exactly what the catalyst does for titanium, it's even more difficult to find an explanation why scandium and cerium would be superior. To some extent, we are still doing black art here. You just have to do series studies. There is no way around it. And all the combinations give you another factor of complexity, and I haven't even talked about these.
Okay, I think we should move on perhaps on that last question, the last talk in the session. We'll begin to clarify some of that. As far as the TM studies, check out our poster. We have the TMs there. Okay, so our next speaker is from Singapore National University, and it's Ping Chen. She's going to tell us about her work with lithium amides.
Thank you. First of all, let me thank the organizing committee to invite me here. My presentation will cover our 5 years experience in the development of metal nitrogen hydrogen system for hydrogen storage. Here's other aspects I'm going to cover in this talk. First of all, is material scope, and a couple of binary systems which will show the reversible hydrogen storage in metal nitrogen hydrogen systems. Then the mechanistic interpretation, our ideas and approaches for the material development, and also a few recently developed systems, and the few things we think is quite a challenge to the practical application and acknowledgement. So first of all, let me introduce the material scope for the metal nitrogen hydrogen system. If we divide the system according to the hydrogen content, we can see there are 3 states. High hydrogen content states, which include amides and hydrides, low hydrogen content states, which normally imides, and lowest hydrogen content states, where we normally encounter the nitrides and nitride hydrides. you can find out the difference between the imide and nitride hydride. In imide, hydrogen bond with nitrogen, and in nitride hydride, hydrogen bond with metal. These are two different chemicals. You can say hydrogen absorption and desorption can be taken place among these three stages. We can absorb hydrogen starting from nitride or nitride hydride and go back to the high hydrogen content state, for example, imide plus hydride. We also can perform hydrogen absorption desorption in between the imide hydride and imides, and also in between imide and nitride hydride, two stages. This is a material scoop. And I would like to show a couple of binary systems which could demonstrate how hydrogen can transfer in between the different hydrogen content stages. First of all, let me introduce the lithium nitrogen hydrogen system. If we start from lithium imide and lithium hydride, we will go to the lithium imide. It's a low hydrogen state compound, lithium imide. And if we mix lithium imide with lithium hydride again, we will finally get lithium nitride. It's the lowest hydrogen content state. But during such a chemical reaction, we can see there's roughly more than 10 weight percentage of hydrogen dissolved from the starting material. And the temperature for the desorption, you can see from this chart, is roughly about 150 degrees Celsius. It's a two-stage desorption processes. And by the PCT measurement, we can say to achieve 1 bar equilibrium desorption pressure, the operating temperature has to be about 250 degrees Celsius. This is a lithium nitrogen hydrogen system. And here comes a calcium system. In this case, we apply calcium imide to react with calcium hydride, and we get hydrogen, which with a solid residue as calcium nitride hydride. It's not imide, it's nitride hydride. The hydrogen absorption, the TPR, and hydrogen desorption occurred at temperature about 400 degrees Celsius. And also look at the PCT files, PCT figures, you can find out the temperature for desorption of 1 bar hydrogen should be about 550 degrees Celsius. And this previous work shows, although there's considerable hydrogen absorption in the binary metal nitrogen hydrogen system, the thermodynamic parameters are not favorable for the practical application. For example, for lithium nitrogen hydrogen system, the heat of formation is greater than 60 kilojoule per mole hydrogen. Therefore, we need to alter the thermodynamic parameters of the system in order to set the heat of formation into a proper range for the operating temperature. To doing that, we either have to alter the heat of formation of reactants or alter the heat of reaction for the products, or both of them. So how to change the thermodynamic parameters, we can adopt two approaches. One is by changing the crystal structure of the starting materials, or we can change the chemical composition of the material. And we are working on the second approaches, how to change the chemical composition of the starting materials or final materials. It's based on our understanding what's the mechanism, how hydrogen can be dissolved from the starting material. Let me use lithium imide and lithium hydride, the interaction between these two compounds as an example. You can say normally alkali metal imide are commonly used deprotonating reagent in organic synthesis. Nitrogen in imide possesses negative charge, and it will execute Coulombic potential to cations. In this case, it's lithium ions. In the same time, hydrogen in imide and hydrogen in hydride possess opposite charge. And the unite of the hydrogen with different charge give very high potential. Thus, we think the chemical driving forces could be both of them. The electrical attraction between nitrogen and cations and high combination potential for the hydrogen. If such an interaction could be a universal interaction, we can, change different amides or different hydrides and synthesize different systems. So first of all, let's look at what kind of starting materials we can choose. We have existing amide which are commercially available, alkali metal amides. We also can make alkali earth amide by ourselves. And more recently, in my laboratory, we found new techniques in synthesized ternary amides. In the same time, we also know there's varieties of hydride. Thus, we can combine different amide and hydride and look at the chemical reaction between these two chemicals. For example, if we fix a lithium amide and react lithium amide with different hydride, we will find out there's hydrogen desorption from such a chemical reaction. And in such chemical reactions, we will also look at the reversibility and the enthalpy of the reaction. Is endothermic or exothermic. Based on our recent experimental results, in those chemical reactions, there's hydrogen desorption, and some of them are reversible, and most of them are endothermic. And the longer the bar means the more heat required for the hydrogen desorption. You can see from this a few chemical reactions, the endothermic properties changes, and some of them exhibit quite good endothermic values. We also can use sodium amide and changing the different hydride. We've got a variety of system which also give hydrogen and also show certain reversibility. One of the interesting features is when we react sodium amide with lithium analyte, we found there's a kind of exothermic reaction. I will touch this reaction in later slides. Also, we can change amide to magnesium amide and also look at all this chemical reaction between magnesium amide with different hydrides. Can see hydrogen can be generated even near room temperature. Here I just put no or yes. Actually, some of the hydrogen can be dissolved near the ambient temperature. Some of them need high temperature. Also, we can use calcium amide to work with different hydrides. And we also can adopt different ternary amides and let them to work with different hydride. By such approach, we can see there should be a variety of systems which could be possible for the hydrogen absorption, desorption, or could be reversible. However, that's not means that really works. It depends on the thermodynamics, the capacity, and also the kinetics, etc. It is still need more investigation in this area. I would like to point out that this approach is one of the few approaches which can be adopted in the material engineering. In this approach, we change different amide and hydride. We also can change the chemical composition of the nitride and also amides. By such a chemical modification, we also can alter the thermodynamic parameters of the system. Therefore, perhaps we can get a very good system hydrogen storage. In the following part, I would like to show a couple of recent examples which shows quite interesting performance in hydrogen desorption and also reversibility. Some of them are reversible. First of all, is a lithium, magnesium, nitrogen hydrogen system. This is quite interesting system and already been investigated by other groups like Sandia and researchers from Japan. In this case, we use magnesium imide to react with lithium hydride. And you can see from the PCT chart, the hydrogen desorption occurs at temperature below 200 degrees Celsius. And at temperature of 180, the desorption pressure is about 20 bars. It is absolutely different from lithium nitrogen hydrogen system. And through one water plot, we notice this system could be operate at temperature below 90 degrees Celsius. However, the kinetic barriers are pretty high. We have worked with Sandia people and find out there's the kinetic energy, the activation energy for hydrogen desorption is about 100 kilojoule per molar hydrogen. So next step should be on the the materials engineering, either on the morphology of the sample or on the introduction of catalyst additives to the system. We also collect several hydrogenated stage and look at the phase transitions in the hydrogen absorption processes, and we find out there's continuous phase changes during hydrogen absorption in the magnesium lithium hydrogen system. The similar work have been done by Sandia groups, and you can look for more details in their poster. We also applied X-ray XPS to look at the nitrogen states in amide form, and we identified 2 nitrogen states in the solid form. That means that the chemical environment of nitrogen could be different, could be at least 2 chemical environment of nitrogen in the solid state. This is a part of the lithium magnesium nitrogen hydrogen system. We also look at the magnesium calcium nitrogen hydrogen system because we want to get rid of lithium. We hope this system could show certain reversibility. However, although the hydrogen desorption amount is pretty good, and we also observe endothermic feature in hydrogen desorption, however, the reversibility is hard to achieve. We think it's probably due to the kinetic barriers. We are working on that. In this chemical reaction, we also observe new phases, new kind of imide formed after hydrogen desorption. And this system, we mix sodium imide with lithium analyte and trying to find out what is going on in the system. It's quite different from a previous system because it is exothermic system, exothermic reaction. We just simply mix these 2 chemicals and conduct temperature program desorption. We notice there's more than 5% of hydrogen desorption at temperature around 110. It is exothermic reaction. Many interesting features involved in such a chemical reactions because we investigate the ball milling process of these 2 chemicals. We put these 2 chemicals into a plenary ball milling and stop the ball milling at different time intervals, collect samples for X-ray and FTIR investigation. We notice there's a stepwise phase transitions during such a chemical reaction. We also identify a new lithium, aluminum, nitrogen, hydrogen solid residues formed after the reaction. So by summarizing these investigations, we realize there's a few steps chemical reaction. The starting material is sodium imide and lithium analyte. At the very beginning, there's cation in exchange between the imide and hydride. You can see after a certain period of time, the lithium analyte changed to a sodium analyte. And in the meantime, ternary imide is formed. Then reaction will continue with hydrogen desorption. We got new analytes. It is not lithium-3 aluminum hydrogen 6 or no, the sodium 3 aluminum hydrogen 6. It is a lithium aluminum 2, lithium sodium 2 aluminum hydrogen 6 is a ternary complex hydride. And finally, we got the new solid state material plus sodium hydrogen and sodium hydrogen aluminum. So overall, we get such a chemical reaction which give us more than 5% of hydrogen release at room temperature. However, its exothermic reaction is hard to be reversible. And this is our another attempt to work on multinary nitrogen hydrogen system. In this case, we use lithium, magnesium, calcium, and investigate the hydrogen absorption, and thermodynamic performance of the system. There's quite a few interesting results. However, the thermodynamic parameters seems not to improve much compared with lithium calcium system. We will continue our research in this area, and hopefully we can reduce the lithium content and also decrease the heat of reaction to shift the reaction temperature from 170 to below 100 degrees Celsius. And I also like to point out that every chemical reaction normally will give us a new solid material. It can be imide, or can be nitride hydride, or can be a new nitride. So by far, the reversible hydrogen storage has been confirmed in this following systems, and some of them, this is only part of them, and some of the systems only give us hydrogen desorption. We haven't achieved the reversibility yet. However, we think if there's continuous effort coming into this area, perhaps we can get a more good system which could be useful for the onboard hydrogen storage. And then I would like to point a little bit on the challenges for the system. It's based on two aspects. One is from scientific aspect, and other from the practical application aspect. By far, there's extremely rare information, and I mean the ground information in this system. Every time we get a new structure, we have to identify the structure by ourselves. No much reference can be referred. And also, we lack thermodynamic parameters which could guide us in controlling and tuning the material's thermodynamic parameters. We also need more investigation into the mechanisms which could give us the origin of the kinetic barrier. By knowing that, we can find out a way to reduce the kinetic barrier. This is from a scientific point of view. From the practical point of view, I think this system has to be carefully evaluated, because most of the nitrogen hydrogen systems are very sensitive to moisture. And if not all, they also quite reactive to carbon dioxide, oxygen, etc. This will pose certain challenge to the practical application. We need high purity hydrogen. We need specially designed containers, etc. And also, if we operate the hydrogen absorption desorption at high temperature, there are competing chemical routes which will give out ammonia. Everyone knows ammonia may not be good for the fuel cells. And this is first things. The second thing is, as you identify from the chemical reactions, there's at least two phases involved in the hydrogenated states. That means after a long time of operation, there's a high possibility for the phase segregation, which will induce slow kinetics, if I'm not wrong. And also we need a good technique to mass product the materials. Nowadays we use ball milling, we use on-site ammonolysis system synthesis. This may not good for the practical production. This is a challenge, as far as I can recognize. However, I would like to say there's a relative system and could be a very broad potential scope for the future exploration. And finally, I would like to acknowledge our financial sponsor and our collaborators. This project has been continuously supported by Agency of Science Technology Research in Singapore in the past 6 years. And last year, we joined the NATO's international joint research collaboration program in hydrogen safely application of hydrogen energy. Our collaboration in a Japanese part is Institute of Applied Energy. We also work very closely with Sandia researchers peoples. We have a pretty good results in lithium magnesium hydrogen system. We probably will continue our collaboration in other systems in the future. I would also acknowledge Professor Wolf from Germany, who gave us very good advice on thermodynamic analysis of systems. Finally, my team members, all these guys are very dedicated and capable people. I'm very lucky to have them. Thank you.
Thank you for a very interesting talk and also for leaving a little time for questions. So, yes, Guido.
Ruckenstein from State University of New York has published some work which talks about use of, I believe, some lithium oxide additives to reduce the kinetic barriers. Could you comment on that and the mechanism by which you think that might work?
You mean some lithium oxide may improve the kinetics of hydrogen absorption, desorption in the lithium nitride system? Am I right? Yeah.
Yes.
By far in the lithium nitride system, I don't think the kinetic part is a critical issues, because we perform absorption, and even at 200 degrees Celsius, hydrogen absorption can be finished within a few minutes. Thus, we haven't performed much work on the improvement of kinetic part in the lithium nitrogen system.
Oh, sorry. I believe it's the decomposition which is accelerated or brought to a lower temperature. Ruckenstein claims that's what I was wondering about.
In the lithium nitrogen hydrogen system, we notice the sample sintering during absorption. Perhaps lithium oxide could be a good additive to avoid the segregation. Thus, will enhance the kinetic for the absorption, I think. Yeah, but we haven't performed this kind of investigation yet.
Thank you.
Well, if there's no more questions, let's thank the speaker again.
The next speaker is Professor Orimo from Tohoku University, who will report about advanced hydrogen storage function of destabilized and mixed complex hydrides. Please.
Thank you, Professor Cantelli. Okay, I'm Orimo from IMR Tohoku University, and my talk is about destabilized and mixed complex hydride. And this work is collaborated with Toyota Central R&D Laboratories, led by Dr. Towata and supported by NEDO, and time to time communicated with some other groups, mainly as the IEA activities. In the project, I have been focusing on the following 4 topics. I mean, how to destabilize the lithium borohydride and the lithium amide as basic materials, and how to optimize the combination of amide and hydride, and also how to prevent or at least suppress the ammonia contamination in hydrogen, and finally, how to effectively provide the new pathways of hydriding or dehydriding reaction on complex hydride. For these purposes, we have been performing, let's say, trinary collaboration. I mean, first theoretical prediction based on the first principle calculation and simulation, and also actual material synthesis using some metallurgical method, and then analysis in many cases in situ analysis, including the precise determination of atomistic and also electronic structure using synchrotron radiation and neutron facility in Japan. Okay, as a result of the collaboration, we have obtained the guideline on these topics. I mean, first, cation with larger electron negativities is effective for the destabilization of the borohydride and nitride system, amide system. And second, one of the optimized combination is amide with lower decomposition temperatures and hydride having faster reaction kinetics with ammonia. And third, not only compositions but also starting materials is important for the prevention or suppression of ammonia contamination. And finally, I can say that it's important to estimate the intermediate phase formed by the dehydriding reaction for the effective provision of new reaction pathways. Okay, in this talk, I'd like to explain these 4 guidelines on the complex hydride. First topic is on the dehydriding of lithium borohydride and lithium amide as basic materials. Okay, here is the dehydriding reactions, both the systems, as Andreas and Dr. Chen have explained. In both cases, so hydrogen concentration is good enough. Again, but dehydriding temperature is sometimes up to 550 Kelvin, although the target of IEA is just 350 Kelvin. That's why we should like to thermodynamically destabilize the booster system, considering the atomistic and also electronic structures. First, I will focus on the lithium amide system. Okay, here is a proposed atomistic structure of lithium amide. So red one is lithium, and green one is nitrogen, and the small blue one is hydrogen. And also we show you the location of atoms in 1,1,0 plane. 1,1 plane.
Use the mouse.
How to? Yeah. Okay. Okay. So here is a location of atoms of 1,1,0 plane, and then we have determined the electronic distribution of the 1,1,0 plane like this. So experimentally and also theoretically. Apparently, lithium is donating electron to the, let's say, NH2 cluster, and the electron is highly localized around the clusters. And also, density of states, I mean the partial density of state of lithium and nitrogen and hydrogen, indicates the charge transfer from lithium cation, let's say cation, to the NH2 anion to stabilize the NH2 clusters. That's why we have proposed that the partial substitution of lithium by the other element with larger electronegativities, like magnesium, is effective way for the destabilization. I will not come into in detail, but this proposal was reasonably supported by the precise calculations. Anyway, based on the proposal, we have synthesized some samples, for example, starting from lithium-magnesium alloys, and then nitrogenation, and then hydrogenation. We knew that somehow hard to produce the single phase of the substitution in case of, especially in case of magnesium. But anyway, we could prove that initial dehydriding temperature, like this, is decreasing with increasing the magnesium concentration down to, let's say, 317 Kelvin, with increasing the magnesium concentration. This technique was also applicable for the borohydride system because electronegativity is also important for the borohydride system. Again, so electronic structure is similar to each other. I mean, the same to that for the amide system. And here's the result. For example, without substitution and also with substitution, just 10% of cation was substituted by magnesium. I'm not trying to increase this amount of substitution. Again, considering the electronegativity is important or sometimes indispensable to widely open the possibility of the complex hydride for the hydrogen storage material, especially on borohydride system like this. Okay, next topic is how to optimize the combination of amide and hydride. Here is a recent progress of the combination of amide and hydride. For example, lithium amide and lithium hydride. Let's say lithium, and calcium, and lithium sodium, and lithium magnesium, and then magnesium and lithium. I mean, in this case, magnesium amide and lithium hydride. So far, at least 2 types of dehydriding processes have been proposed. First one is redox process, as Dr. Chen explained. And the second one is ammonia mediating process. In this process, here was arrow, just arrow. In the first step, the amide change into the imide or sometimes nitride to form the ammonia-like phase. And as a second step, and this hydride, metal hydride, react with this ammonia-like phase to form the actual hydrogen. This proposal was made by Dr. Fu and Dr. Ichika's paper. If we would take this process, we can we can select or we can optimize this blue M and red M independently. For example, as a first step, the point is to find out the metal amide with, let's say, blue M here, with lower decomposition temperatures to easily form the ammonia-like phase. And then we did experiment. Here is a result of some gravimetry for sodium aronate and lithium and magnesium aronate. We can see the decomposition temperature is lower in this order. That's why we select magnesium amide here, magnesium for blue M. And second step, this point is to find out the metal hydride having faster reaction kinetics with ammonia. And also, we have confirmed that lithium hydride, sodium hydride, and magnesium hydride can react with ammonia completely. But the kinetics is so big different. So, I mean, lithium hydride has much faster kinetics, even in the lower temperatures. That's why we have selected the lithium for red M. So now, the optimized combination is magnesium amide with lower decomposition temperature and lithium hydride having faster kinetics, reaction kinetics with ammonia. Now, next question appears. I mean, how is the composition ratio? This matter is closely related with the next topics. I mean, how to prevent or how to suppress the ammonia contamination. Here is just simple yes and or no chart for hydrogen and ammonia emissions or from these combinations. If this X, I mean the ratio of lithium hydride is equal to 4 or more than 4, ammonia-like phase from amide, in this case magnesium amide, can react with lithium hydride. So in this case, somehow easy to come to here. I mean the form only the hydrogen. If the X is less than 4, in some conditions, I mean in case of higher temperatures, some part of ammonia-like phase cannot react with lithium hydride. In that case, so come to here. So the actual ammonia, gas phase ammonia will be formed. It's highly toxic for the FC reactions. So in this case, we can just heat up the sample at moderate temperatures, or adding catalyst, or heating slowly also to come to here. But in any case, keeping from air is important. Otherwise, come to here again. So here's our actual result on the hydrogen and ammonia emissions. Here's a result of TG, and also here's a result of mass spectroscopy. Simply speaking, that the amount of ammonia formation can be suppressed with increasing the amount of X, with increasing the amount of lithium hydride. But in this case, not only composition, but also the starting materials is important. In case of specific samples, we can very much suppress the ammonia formation. This combination, the magnesium amide and lithium hydride can be formed just by the hydrogenation of the mixture of nitride. In that case, I just simply guess that elemental dispersion is good enough not to form ammonia so much. But I just think that there may be a still open question on the ammonia mediating process. For example, Professor Fuji's group just recently did quite nice experiment to see the in situ IR measurement. And what I'd like to say here is this ammonia mediating process is affected. Excuse me. Maybe 20, okay. Again, just reviewing. Okay, come here. And again, I personally think that the ammonia mediating process is highly affected not only by the composition, but also the starting materials. How elemental dispersion is good or not. So also, atmospheres or heating rate or open or closed system. The extrinsic factor is also important to think about the ammonia mediating process. So we hope to have a very careful discussion on these matters. Anyway, back to the hydrogen emission. We have measured the PCT properties on these samples, and we have also confirmed the reversibility just by heating this sample. Also, we did a precise study on each step of the dehydriding reaction of the combination of amide and hydride, experimentally and also theoretically. I can say that it's quite complicated, but what I'd like to propose here is that this composition ratio, this value of X, can be selected depending on the application condition. Which temperature we can heat up the sample, or how sensitive to the ammonia, or how much hydrogen we need also. Again, so X is, let's say, tunable from 2 up to 4, depending on the application condition. I think it's one of the advantage to think about the complex hydride for the hydrogen storage materials. Okay, now the final topics is how to provide the new reaction pathway. I'm now very interested in the mixing effect. In case of lithium amide, it decomposes into the lithium imide or nitride, as Dr. Chen explained, around 600 Kelvin. But also lithium hydride change into the lithium and the hydrogen. In this case, the dehydriding reaction occurs more than 900 Kelvin. But just by mixing, the decomposition or dehydriding temperature reduce so much. like this. But this is a mixing effect, but it does not always happen. I mean, the point is to estimate if there is any intermediate phase after or even during the dehydrating reaction. For example, the combination of lithium borohydride and lithium amide, there is an intermediate phase like lithium BNH systems. But in case of lithium borohydride and lithium alanate, there is no intermediate phase. So in this case, a mixing effect may not occur. Now, we focus on the combination of lithium borohydride and lithium amide. In this case, we have confirmed that the dehydrating temperature decrease so much, more than 200 Kelvin, and also the dehydrating temperature one order increase even in the lower temperatures. Apparently, lithium borohydride was destabilized by the mixing with lithium amide system. Also, we have been focused on this intermediate phase, lithium BNH system, for realizing the reversible dehydrating and rehydrating reactions. Also, Dr. Pinkerton's paper also pointed out the importance of this intermediate phase. We have already determined the atomistic structure of this 3128 phase like this, and found that it's non-conventional complex hydride. I mean, forming the ordered BH4 and NH2, only by the one type of cations. Again, so it's quite interesting structure because two variation of amide, two variation of anion per one cations. I think it's first case on the complex hydride. Anyway, we have found another type of such kind of non-conventional complex hydride, which may show the reversible dehydrating and dehydrating reactions. We'll see that. Anyway, the focusing on mixing effect is now important research direction to destabilize or to promote the dehydrating reaction. Not only complex hydride, but also some types of ionic compounds. And here is a recent progress. Please check that. Okay, again, based on the, let's say, trinary collaboration, we have obtained 4 guidelines on the complex hydride as hydrogen storage materials, like this. And here is a recent publication on the series and material synthesis and analysis. Thank you very much for your kind attention.
Thank you very much, Professor Rimo. The paper is now open for discussion. Are there any questions? Questions? Okay, Craig?
Oh, just like to mention, you know, at the very end of your talk, you showed the John Vallejo system there with the lithium borohydride and magnesium hydride. But what's exciting about that is the fact that it's reversible.
Yeah, that's right.
And I wonder if there's any guiding principles on these, which ones might you anticipate to be reversible?
Okay. Of course, I'd like to find out a reversible system. And some type of lithium BNH system is reversible. So we'll see that.
Thank you. Next paper is experimental investigations of heat and mass transfer processes in metal hydride porous bed or hydrogen storage and purification unit, presented by Dr. Borzenko from Russian Academy of Sciences, Russia.
Good afternoon, ladies and gentlemen. The presentation I'm going to make deals with what's going on in the field of experimental investigations of heat and mass transfer processes in metal hydride porous beds of hydrogen storage and purification unit. And this research is done by a laboratory of intensification of thermal processes of Institute for High Temperatures of Russian Academy of Sciences. So it's quite evident, I think, that heat and mass transfer in metal hydride porous beds greatly affects hydrogen storage and purification devices efficiency, and that understanding of heat and mass transfer peculiarities in micro and nanostructured materials, adsorption process with big volumetric and thermal effects is lacking, and we need adequate mathematical models and the experimental verification to optimize reversible solid-state material hydrogen storage systems. So, what are the basic peculiarities of heat and mass transfer process at hydrogen sorption in metal hydride porous media? So first of all is a big thermal effect of reaction and the necessity to arrange efficient heat removal and heat application to the porous bed. The second is low effective thermal conductivity of metal hydride beds, volumetric effect connected with the change of particle bed volume during the reaction, and the influence of non-absorbable admixtures on effective thermal conductivity and thereby on the efficiency of the storage and purification unit. So the next slide is just a brief overview of the activity of our laboratory in this field. We do wide-scale investigations of heat and mass transfer, of development and experimental verification of new engineering solutions for metal hydride storage and purification units, such as variation of heat exchanger design, operation mode optimization, system integration and hydrogen storage for different applications such as fuel cell power supply systems, numerical modeling of the porous media, and the modeling of heat and mass transfer process in metal hydride porous beds. This is in collaboration with Moscow Power and Engineering Institute. So speaking about the model we have on this, I would recommend you to visit to see the poster of my colleague, Dr. Lazarev. He will describe everything in details, and I will just show some of the modeling results. So, as we do both experimental and theoretical study, we manufacture and we do various types of heat exchangers for further tests in our test bench. This is the result of numerical modeling of the similar geometries. This is mass concentration, not mole. This is a mistake. So first is just cylinder with the outer wall cooled, and on the axis there is another cooler by cold water. Fins, blue line is the same with fins, just to enhance heat transfer, and the red line, you will see the picture a little bit further. This is the matrix of small coolers in a bed of metal hydride. So the result of this modeling shows that the use of the fins results in increase of 8% at charging time of 10 minutes, and the use of tube matrix is 40% at charging time of 10 minutes. Speaking about the influence of admixture, which is quite important for all this technology, we modeled several operation regimes. Here you can see the results of absorption of pure hydrogen, absorption of gas admixture with 5% of noble gases. This is calculation for 5 kilo AB5 type alloy, and resulting from this we came to a conclusion that if we want to have an efficient cleaning system, we have to use pressure swing adsorption mode. So this is just means the periodical expulsion, which increases the efficiency of the metal hydride reactor. So this is just to demonstrate you. Here we can see the gas, the field of gas temperature for 3 variants of metal hydride unit heat exchanger design after 10 and after 600 seconds of adsorption process for all the mentioned 3 types of reactor. This is annular reactor, this is annular with metal pins, and this is the matrix of small coolers, and you can see the result that its temperature is not that radically different like here, and we get better result as well as from the point of view of better cooling, and also from the point of view of mass concentration and on the capacity and the charge time. So this is how the model works. To verify the model and to continue our research, we created experimental facility for complex investigations of solid-state reversible hydrogen storage and purification in hydrogen storage purification systems. This is a test bench for optimization of purification and storage systems. With purification we have here at present about 10 kilo of metal hydride, and the storage device is 159 kilo of AB5 alloy. It consists of preliminary cleaning system, which is deoxygenizer and dryer to get rid of oxygen and to get rid of vapor. After that we have fine purification system, which is metal hydride purification system, AB5 type alloy, you can see it here. And we have the storage device, which is also, you can see the composition here, working in similar pressures and similar temperatures. This is the device is fed by clean hydrogen. So some results of our experimental activity. Here you can see the absorption cycle of metal hydride purification unit. We have a measurement, a diagnostic system gives a complete measurement of what's going on inside the reactor, including the volume flow, the pressure in the device, and the temperature field. We have both in radial and axis direction. We have thermal resistors. As for this, exactly this case, they are situated like here in the bed, near the outer wall of the cartridge and on the inner wall of the cartridge. Here is a desorption cycle with changing of flow, outlet flow, to see the response of the system to transitions. Here you can see the average capacity and the parameters, geometry of the storage unit we have. It consists of 13 such kind of cylinders. They don't have diagnostics, they're just a storage device, and with average capacity of 0.42 grams per second. As for the cleaning system, we got about 1.35 mass percent of hydrogen contents in metal hydride. So since we had all the components for the fueling system we have a preliminary cleaning, fine cleaning, we have a storage device. So an idea appeared to integrate it in a hydrogen storage device for fuel cell power supply system. And that's what we are working at now. We have a PAM commercial 5 kilo fuel cell. And we hope that in some time this will help us to optimize the regimes of fuel cell fueling system due to estimation of all the heat losses we have, due to better operation regime, and we can try to increase the overall efficiency of the refueling systems. As for heat transfer and system analysis, we believe that here is some reserve for metal hydride to be more efficient as a storage. New materials, they are very good we need the new materials, but also much attention must be paid to heat transfer and to system integration, exergy, efficiency. To conclude with, I would say that the created experimental facility for complex investigations of solid-state reversible hydrogen storage and purification systems, together with the developed 2D and 3D numerical model of heat and mass transfer, its option, form a tool for solving the task of efficiency improving of metal hydride, hydrogen storage and purification devices, for the development of new reactor types optimized for fast recharge and hydrogen purification, and for the development of reversible solid-state hydrogen storage for PEM fuel cell power supply system with advanced thermal management, optimized power load modes and transient response. So, concluding, I would say thank you to the organizers of the conference and to the Department of Energy for making our participation happen. Thank you very much.
Thank you very much. Are there any questions? We have some time for questions. Any questions? So then, thank you very much, Dr. Borzenko. Before closing this session, I would like to ask the colleagues, Professor Mori, Wang, and Greason, to join us here at the table after the coffee break. We will have a coffee break of 30 minutes, therefore, please come back here at 5 minutes. Thank you very much.
Holding back the
Okay, ja, das hatten wir vor einer Zeit. Du musst dann eine Einladung bekommen. Ja, bist du da zurück, oder?